If you're anything like me, you've always wondered how do black holes actually form. I mean, they're mysterious objects in space that can literally suck in anything, even light. So how do they form? Well, we know that all planets and stars form from giant clouds of dust and gas called nebulas. And we know that at the center of every solar system is a star that is massive and hot enough to create and maintain a strong gravitational pull. This keeps all the planets in orbit around it. But what happens when a star collapses? Does it explode into a supernova and dissipate into the universe? Or does it keep its shape and just get smaller? Well, the answer depends on the mass of the star. If the star is about the size of our sun or smaller, then when it collapses, it will simply dissipate into space as a white dwarf. But if the star is much more massive than our sun, say 20 times larger, then when it collapses, it will not only create a big explosion called a supernova, but it will also create a region where gravity is so strong that nothing, not even light, can escape, collapsing the star into an infinitely dense point called a singularity. This is what we call a black hole. So we know that black holes form from the collapse of massive stars, but how do these massive stars form in the first place? Well, this is where things get really interesting because it turns out that the way stars form has a lot to do with the environment in which they form. You see, for a star to form from a cloud of dust and gas, two things need to happen. First, the particles in the cloud need to come together and start colliding with each other. And second, the collisions need to be frequent enough that the particles can stick together and form larger and larger clumps. The problem is, the bigger these clumps get, the more pressure they exert on each other. And the bigger the pressure gets, the more the particles in the cloud want to fly away from each other. So there needs to be some force strong enough to hold these particles together as they form larger and larger clumps. And this is where the environment comes in. If the cloud of dust and gas is in a very dense area of space, then the particles won't be able to fly away from each other because there's not enough space. But if the cloud is in a low-density area of space, then the particles will have a much easier time flying away from each other. In fact, if the cloud is in a low-density area of space and the particles in it are moving too fast, then the cloud will just dissipate into space and never form any stars at all. So for stars to form, there needs to be a balance between the force that brings the particles together and the force that pushes them apart. If the force bringing the particles together is too weak, then the particles won't collide often enough to form clumps. But if the force pushing the particles apart is too strong, then the particles will fly away from each other before they can form clumps. This balance is what astronomers call hydrostatic equilibrium. It's the same principle that keeps a ball floating in the air. The force of gravity pulls the ball down, but the force of the air pushing up on the ball keeps it from falling. When the particles in a cloud of dust and gas are close enough together, the force of gravity is stronger than the forces pushing the particles apart. So the particles can come together and form clumps. These clumps can then go on to form stars. But once the star forms, it's really important to remember that it's still mostly empty space. You can think of it kind of like a balloon. Even though there's a lot of air inside of it, there's still a lot of empty space inside of it. And the reason why this is important is because when a star starts to collapse, it's the outer layers of the star that collapse first. As these outer layers collapse, they're drawn towards the center of the star. And the closer they get to the center, the stronger the gravitational pull they feel. At some point, the gravitational pull at the center of the star is strong enough to overcome the force that's holding the star together. And once that happens, the star collapses in on itself. The thing is, even though the star may seem like it's getting smaller, it's really just getting denser because most of the star is still empty space. It's like when you squeeze a balloon, it may seem like it's getting smaller, but really you're just pushing the air inside of it closer together. The problem is, when a massive star collapses, it doesn't just get denser, it gets incredibly dense. In fact, at the center of the star, the density becomes infinite. That's because as the star collapses, all of its mass is being squeezed into a smaller and smaller volume. This means that at the center of the star, the pressure and temperature become incredibly high. And it's this high pressure and high temperature that creates the energy needed to make all the elements heavier than iron. You see, stars make energy by fusing lighter elements into heavier ones. When a star first forms, it starts fusing hydrogen into helium. Then when it runs out of hydrogen, it starts fusing helium into carbon. And when it runs out of helium, it starts fusing carbon into oxygen. And so on. The problem is, when a massive star reaches the end of its life, it can no longer fuse elements because it doesn't have enough energy. That's why when a massive star collapses, it does one last big fusion dance. It fuses iron into elements heavier than iron, which releases even more energy than normal fusion. This energy is what makes a supernova explosion so bright. It's like when you burn a log in a fire, the hottest part of the flame is right where the wood is burning. But here's the thing, when a massive star collapses, the explosion isn't big enough to make elements heavier than iron. In fact, it only makes elements up to zinc. So even though a massive star goes through one last big fusion dance when it collapses, it doesn't make any new elements. That's why when a massive star collapses and forms a black hole, all that's left behind is a bunch of heavy elements, like iron, nickel and zinc. These elements are what we call the iron peak elements because they're the heaviest elements that can be made in a star. Now, even though these elements can't be made into anything heavier inside of a star, they can be made into something heavier when a star explodes as a supernova. That's because during a supernova explosion, the elements in the star are blasted into space at incredible speeds. And when these elements collide with other elements in space, they can form new elements. For example, if iron from a supernova explosion collides with a neutron, it can form manganese. These supernova explosions are what we call pair production events because during the collision, an electron and a positron are created. This means that the number of protons and neutrons in the universe is increasing over time. And this is important because it turns out that the rate at which new elements are being formed in the universe depends on the number of protons and neutrons available. Now, I know that sounds kind of crazy, but let me explain. You see, every element in the universe is made up of some combination of protons and neutrons. For example, hydrogen is just one proton and one electron. Helium is 2 protons and 2 neutrons and 2 electrons. Lithium is 3 protons, 4 neutrons and 3 electrons. And so on. So if you want to make a new element, you need to have a bunch of protons and neutrons available to work with. Now, in the early universe, there were lots of protons and neutrons available, which is why so many elements were formed in those days. But as the universe expanded and cooled, the number of protons and neutrons available decreased. That's why most of the elements that are formed today are on the iron peak. But that doesn't mean that elements heavier than iron aren't being formed. They are. It's just that they're being formed at a much slower rate. So even though black holes don't make new elements, they do play a role in the production of elements heavier than iron. And that's how we get elements heavier and heavier than uranium, plutonium and even einsteinium. Of course, these super heavy elements are very rare. In fact, they're so rare that we've never found them in nature. We've only been able to synthesize them in labs using particle accelerators. But that doesn't mean they don't exist. They do exist. It's just that they're so unstable that they decay into different elements almost immediately. In fact, the heaviest element that has ever been synthesized is oganesson, which has an atomic number of 118. That means that every atom of oganesson has 118 protons and 118 neutrons. And even though oganesson is synthetic, scientists believe that it occurs naturally in some places in the universe. So who knows? Maybe one day we'll find a black hole that has a bunch of oganesson in it. Hey, if you like this video, check out my other videos. And thanks for watching.